One of the questions we ask regularly is, how do we make data-driven decisions? How do I know that I'm making a decision that is supported by the information I can gather? All right. I'm going to pull an example out of thin air. One of the former faculty members here at Seton Hill, I never saw her without a can of Monster in her hand. Ever. I don't care if it was 7 in the morning or 10 o'clock at night. I never saw her without a Monster Energy drink in her hand. And so I said to myself, I wonder how many of these she drinks in a day. And I asked her, and she said the average was about 5. Yeah, that was my reaction. What the? So I said to myself, is that unusual? Is 5 out of the realm of reasonable for somebody to be drinking? 5 Monster Energies a day. I don't know the answer to that. But I could find out. I could survey a whole bunch of people at different ages, different jobs, and ask, how many do you drink a day? How much caffeine do you take in? How many energy drinks do you drink? One of my coworkers' children is on a college sports team, and their sports team is sponsored by Celsius. He gets it by the case. Again, my question is, how many? How many? I don't know. But if I had an idea, I could then formulate a hypothesis. And I could say, I think on average, people drink 2 of these a day. Maybe I'm right, maybe I'm wrong. Then I can construct a survey and gather some data. I can analyze the data and I can see whether or not that one person's number of 5 is outrageous or within reasonable. There's a data cycle. Page 318 talks about that idea. I get an idea. I think people drink 2 energy drinks a day. I formulate that's my hypothesis. I gather data. I create a test statistic. And I say, is my number that I expect in my hypothesis matching this data, yes or no? I make a decision about that. And then I revise my idea's results. And I can go back and do this over and over and get a better idea of what's going on and make a decision in my data behavior to make a business decision. Should I be selling more of those on campus? Should I be selling less of them on campus? Should I be stocking them differently? Maybe I should have them in different locations, whatever it is. But in order to do this, I have to have an idea, and then I have to have a hypothesis. Hypothesis testing. Now, my hypothesis could be whatever the average number of energy drinks is. It could regard to anything. I'm going to call my assumption the null hypothesis, H0, or H null if you want. And that's if I'm right. If I'm wrong, that's the alternate. Now, in order for me to do this right, these 2 hypotheses have to be 2 things. They have to be mutually exclusive. I've heard that phrase before. Where have I heard the idea of mutually exclusive before? It's in this course. This is not something from outside. Where in this course have we used that phrase before? Aha, mutually exclusive events come out of our probability idea. It's more than there's no intersection. It's that if you have one, you can't have the other. So either H1 or H0 is true, never both. And they have to be exhaustive. Exhaustive means we exhaust all the possibilities. Everything that happens, either I'm right or I'm wrong, there's no middle ground. And that covers all possible behavior. With regard to this specific hypothesis. So, in terms of, I go to a trial, somebody's guilty or not guilty. Those are the only two outcomes in a trial. Whether they're guilty because of a plea or whatever, there's either guilty or they aren't. That's what the end result of a trial is. I flip a coin. It either lands heads or tails, nothing in between. Exhaustive, mutually exclusive events. I believe the average number of energy drinks consumed by a person is 2. Either I'm right, and the average is 2, or I'm wrong, the average isn't 2. There's no other choice, and every possible result is covered there. The drug test was positive, the drug test was negative. The security alert went off, or it didn't. Somewhere in here, though, I have to have a decision rule. The decision rule allows me to decide whether or not I think my hypothesis is right or wrong. Statistical analysis doesn't prove something. It either supports or does not support my decision. But I can't prove something here. And I always phrase this idea as whether or not I should reject my assumption or not. In a trial, that's the judge's instructions on is someone guilty beyond a reasonable doubt. In a drug test, it's did the urine sample or blood sample or hair sample contain enough markers for the drugs for me to say drugs were in this system. In a security system, the user has more discrepancy. The password is off by this many letters or more. The badge number reads incorrectly with this many errors or not. I need some sort of a decision rule. I then gather my data, I make my decision. But I phrase it not as I am right or I am wrong, but my assumption was supported by the data or rejected by the data. Not proved by. And in most of these tests, I can test something over and over and over again. I can take multiple drug tests. I can go through multiple security scans. The only one I really can't do it on is a trial. There's this thing called double jeopardy. You can only be tried for a crime once, right? But I don't actually ever prove things with statistics. So now the question is, how do I do this? What's the procedure for doing this? And what are the actual numerical ideas that we get? Questions? It's important to decide, when we figure out what our decision rule is, it's important to decide which way we want to make our mistake. Do we want to err on the side of caution and require a lot of confirmation to support our hypothesis? Or do we want to err the other way and say, no, we'll be more likely to reject it? So let's talk about error. Okay. I have a hypothesis about energy drinks. On average, people drink 2 a day. Either I go out and I measure and people do drink 2 a day, or people drink something other than 2 a day. So either my hypothesis is true or false. Problem is, I don't know whether it's true or false. I just get some data to support whether I think it's true or false. And then I get to decide, what do I think? Well, that's giving me 2 options over here. Either I think, no, you should reject the hypothesis, or you should accept it. So really, there are 4 options here. If it's true and I accept it, then I've made a good choice. If it's false and I reject it, I've made a good choice. So really the questions are, what goes in those other 2 boxes? And we used these terms before in our decision tree discussion. I say no, but the result was actually true. That's called a type 1 error. I say yes, and the result is actually false. That's a type 2 error. I don't have perfect information, so I don't know whether I've made one of these errors or not until much later on. A type 1 error is a false positive. I rejected something that was true. A type 2 error is a false negative. I believed something that was false. Now, my goal is to make as few mistakes as possible. So I would like those 2 boxes in the type 1 and type 2 error to be as small as I can make them. That depends on the consequences, though, doesn't it? I have a drug testing regimen for NCAA athletes, right? If you're a Div 2 athlete, you get drug tested. If I make a type 1 error, what happens to that athlete? They get suspended in spite of not having done anything. They're disqualified and they're clean. So I accepted a false positive test. On the other hand, down here, what's a type 2 error consequence there? They get to play and they still took drugs. So they get to cheat. And we didn't catch them. Which consequences do you think, and this is a value judgment, which consequence do you think is more severe? I don't know the answer to that. Is it worse to have somebody clean not play, or is it worse to have somebody dirty playing? Is it worse to have that person who's clean with a positive drug test on their record? Or is it worse to have the person who's a drug user standing up there as a bastion of the sport? The value judgment. And it's up to the NCAA and the sporting communities and the coaches and the players to make the decision as to which is more of a problem. If I'm looking at a security system, a type 1 error, oh, I went to swipe my card and it didn't let me in. I went to tap on the door to get into the building and it said, no, you don't get to go in here. But I'm allowed. I rejected your permission to come in. Somebody who's authorized to use the building can't get in. What's this one? I let someone unauthorized in. Now again, I'm pretty sure the administration building is not holding the secrets to life, the universe, and everything. So having an unauthorized person wander around here might not be as bad, say, as an unauthorized person wandering around the Pentagon. Security system is different, right? But I'm pretty sure I want this error to be less common than this error. So a failure to swipe in where I had to tap my card twice or more to get in is a little more acceptable to me than letting someone in spite of them not being authorized. So what we have to decide is our level of significance. I've heard that phrase before. I'm going to have some significance level. I'm going to call it alpha. And alpha is given by the chance that I reject the null hypothesis given that that hypothesis is true. Look, I'll even state it as a conditional probability like we did back in chapter 5. That is the chance of being in this box. That's the chance of a type 1 error. I'm going to call beta the chance that I fail to reject the null hypothesis when that null hypothesis is false. What's another way to write this chance in terms of these options up here? Say again? It's the chance of a type 2 error. So somewhere in your notes, you've got that little 2x2 grid up there. Keep that at hand, but keep these numbers at hand as well, alpha and beta. On the other hand, what I really want is to have this number be small and this number be small. Problem is there's a trade-off here. By decreasing alpha, I tend to increase beta. Decreasing alpha means I make it harder to reject. I'm more likely to fail to reject. But if I'm more likely to fail to reject, that's going to make beta go up. If I make beta go down, I make it harder to fail to reject, then I'm more likely to reject. And then alpha goes up. On the other hand, the chance that I get it right, the chance of a good choice, would be 1 minus alpha. I rejected it, and it was false. This is usually referred to. Oh, wait a second. That's 1 minus beta, not 1 minus alpha. 1 minus beta. Got to write down the right number. 1 minus beta. It's called the sensitivity or the power. The more powerful test, the more likely I am to reject my H0, but then I'll detect more problematic things. The more power I get, the lower beta gets. But that makes the rejection harder. And that means this is a problem. Think about our security system. If I want to make the type 2 errors small, then I make it harder to get in. That means more people have to tap more than once. I reject more good credentials. That's type 1 error. So there's a trade-off there. A more sensitive smoke detector. Would make sense to have a really sensitive smoke detector, wouldn't it? Okay, here's a question for you. How many of you live on campus? How many of you have had the wonderful privilege of standing outside at 2 o'clock in the morning because the stupid fire alarm went off? The more sensitive the smoke detector is, the more likely it is to have a false alarm. And I mean, to the point where somebody using hairspray in the bathroom could set off the smoke detector right outside the bathroom because the sensor detects the molecules from the hairspray going into it. Oops. Whoop, whoop, everybody out. I don't care that it's 3 o'clock in the morning in February and it's snowing. Out you go. How many of you had to take a COVID test sometime in the past 5 years? I want you to imagine a more sensitive COVID test. More people will be healthy, right? Because they'll find out they have COVID and they'll stay home. More sensitive COVID tests would also result in more false positive tests. You have the barest itty bitty bit of COVID in your system. Yeah, I walked past somebody who sneezed last week. You're not infectious. You're not capable of giving COVID to anybody else. You don't show any symptoms of the disease, but you've got a little bit in there. You're positive, stay home. You're quarantined for 10 days. So there's a trade-off between powerful tests and type 1 errors. I'm usually more concerned with false positives. I usually want my false positives to be as low as possible. But if I do that, I run the risk of false negatives. How can I reduce false negatives? Well, I could gather more evidence. Instead of taking one COVID test, you have to take 2. Each one's a little less sensitive, but I'm sure you've got it if you hit it twice. But by gathering more evidence, that costs more money, right? COVID tests at the moment are not free. So if I go buy, I have to buy more because I have to take them once. I'm in a problem here. So let's think about our errors. Problem 5, page 323. What is the consequence of a false negative in an inspection of your brakes? You go out and you get your brakes inspected. The null hypothesis is the status quo. Your brakes are fine. What's a false negative mean in that setting? This is why you have the definitions in front of you. A false negative occurs when? So a false negative means we thought it was okay. We didn't reject our hypothesis. We think things are okay. I think your brakes are fine, but I made a mistake. What happens? Crash. Somebody gets really hurt. Your car gets destroyed. Your brakes don't work in the wrong time. What's the problem with a type 1 error in that situation? I pay for a brake job in spite of not needing it. So, which is the worst trade-off? That I have to pay for a brake job or that I total my car from bad brakes? Okay, I'd much rather have a false positive than a false negative in that case. In each and every one of these settings, I need to figure out which error is going to be worse so I know what kind of a test I'm looking for. Questions? More often than using false positive, false negative, type 1 and type 2 is the standard descriptor. So I'll talk about a type 1 error. We need to know what that means. Type 1 means I rejected when I shouldn't have. Type 2 means I didn't reject when I should have. Okay. Usually, I choose my significance, alpha, based on my willingness to bear the cost of a false positive, which in this case was the cost of a brake job, right? So I say to myself, I would rather pay for a brake job than have people crash. So if you have questions about the brakes, tell them they need a brake job. In a trial, we even wrote it into the law. I assume you are guilty, you are innocent, unless a preponderance of the evidence beyond a reasonable doubt allows me to think you are guilty. The presumption of innocence. And the cost of that, the cost of the false positive, is I send an innocent person to jail. The cost of a false negative, somebody who committed the crime goes free. As a society, we decided and made it a matter of constitutional law that I would rather have a type 1 error than a type 2 error. But I'm not usually speaking of trials or brake jobs. I'm usually thinking of business decisions, and I'm usually thinking about numbers. So I start to think about all of this in statistical terms. A statistical hypothesis, in particular, is a statement about a parameter in the population, the average, a proportion, a standard deviation even. I want to know something about this population. I want to understand more. How many average energy drinks in a person? To figure out whether my hypothesis is supported or not, I do a hypothesis test with a null hypothesis and an alternative hypothesis. So, how do I do this? How do I do a hypothesis test that allows me to decide between my assumption, the null hypothesis, and rejecting that assumption, the alternative hypothesis? If I say that I believe the average number of energy drinks a person drinks is 2, then I go take a sample. So that's my decision about energy drinks. That's my assumption. I think the average should be 2. I go take a sample, and I compute a statistic about that idea. In this case, since I'm thinking about an average in the population, that's why I used mu, I'll take a sample and I'll compute the sample mean, X bar. Question: what would you expect X bar to look like if your hypothesis is correct? It should be close to 2, right? It might not be exactly 2. Remember, we have sampling variability. We talked about this when we talked about confidence intervals in the last chapter. I've got the ability, when I take a sample, some might be off a little bit on either side. So maybe I'll get in my result, I'll get 1.9. Maybe I'll get 2.3. Maybe I'll get 6.7. So now I can ask, how close is this to this? And that's exactly what we were talking about in the previous chapter. I can look at the sampling distribution, the standard error, and I can say, hey, is this far enough away or close to my hypothesized value to reject the idea that my average is 2? So my decision is, do I reject the idea that the average is 2, or do I accept the idea the average is 2? If I got 6.7, I'm probably going to say, whoa, that group of people is jacked up. If I got 0, every single person I ask doesn't drink any energy drinks at all, I might say the same thing. That's too far away from my assumed value for me to think I'm right. How do I make that decision? I'm going to do proportions later. So let me think just for the moment about a mean. For a mean, a null hypothesis comes in 3 flavors. The one I've been talking about so far is that I think the average is some given value. But I could also ask the question, is the average number of energy drinks a person drinks less than or equal to 2? Or is the average number of energy drinks bigger than or equal to 2? Now, instead of using the number 2, I use this mu0. Mu0 is my hypothesized value. So for my example about energy drinks, it's 2. But it could be any number depending on the situation. The average cost of a brake job, we were just talking about brake jobs, right? The average cost of a brake job is under $700. True or false? How am I supposed to know? But I can gather data and I could say, hey, is it less than or equal to 700? Now, these are my null hypotheses. So these are H0. Every null hypothesis has a corresponding alternate hypothesis, H1. For each of these, what's the right statement for H1? Wait a second. H1 versus H0, they have to be mutually exclusive and they have to be exhaustive. So that means I have to take out all the possibilities and they can't happen at the same time. So what's the opposite statement from this one? That mu is greater than that number. What's the opposite in this case? It's not equal to. And what's the opposite in this case? Now, all of a sudden, I have the most amazing sense of deja vu. My brain, I say, I've seen this crap before. Let's call it deja vu. Okay, I've seen this garbage somewhere. A number less than some threshold. A number bigger than some threshold. Okay, I know I've done something like this before. But in particular, I'm now doing it for a sampling distribution. What did we say about sampling distributions in the last chapter? Y'all were here for the last chapter, right? I didn't hallucinate you all into being. What did we say about sampling distributions in the last chapter? Here's a hint. Central limit theorem. For a mean, that's what I'm talking about here, means. For a mean, central limit theorem says our sampling distribution looks like adjective, a normal distribution with a standard deviation given by the standard error. So the bigger my sample, the narrower that curve got, right? But that means I'm asking you, hey, are we below some value? Are we above some value? These pictures should be drawn on a normal curve. These three sets of hypotheses are based on these ideas, these three alternate hypotheses. My mean is too big I said the average was 2. I did my test. I got 6.7. My mean is not equal to. I did a test. I got 1.2. My mean is too small. I did a test. I gathered my data. I got 0. And all 3 of those go with normal distribution pictures. Here, I'm too far to the left. Here, I'm too far to the right. In the alternate cases, so we call this a left tail test. We call this a right tail test. And it's because of the alternate hypothesis being too small on the left, too big on the right. This one, it can go in either direction, right? So we're going to call this one two-tail. Because not equals means you could be not equal on the left or not equal on the right. Then, all of a sudden in my head, I have a picture. I have a normal distribution picture. You made them for the exam. You made them for the notes. I have this picture on page 325. And all of a sudden, this tells me how hypothesis testing works. Look at what they've labeled the rejection piece in the left test. If the number you get is far enough away to be in this little bitty area here of your sensitivity, how sensitive is your test, that's our alpha value. If it's way down there on the left, we reject. And that means I need to know what this critical value is. But that critical value is a Z. I'm too far off to the right. I'm in this little critical region over here. This is some Z value. If my Z value for the number I calculated is too big, then I reject my null hypothesis. Here's the two-tail. Hey, wait a minute. How much area is in each tail? Alpha over 2. Just like the confidence intervals, right? The alpha over 2 on each side. Son of a... Hypothesis testing says I'm outside the confidence interval. I'm no longer confident that I'm right. Reject the hypothesis. This is the exact mirror image of what we just finished doing. So I need to create my test statistic. I need to figure out what this critical value is. And then I can say yes, reject the hypothesis, or no, don't. We'll do several more examples on Friday. Please remember you have homework for Chapter 8 due on Friday. If you have questions, I do not have office hours in person tomorrow. I have them tonight remotely. I will see you all then. Have a wonderful day.